Hey students, how you doing? Mr. Elliott here, and I'm going to try to do right now our second video lesson. Now, before we get into the video lesson, let's just talk techniques. What could you be doing to better yourself as I'm trying to teach these lessons? Let me shrink Elliott here. Ooh, lovely. Option one. And option one, this is what's recommended. This is what will make you the best student moving forward, and that would be to write your own notes. It helps. Practice will make perfect. And if you feel that the lesson's moving too fast, you could always pause the video, catch up with the notes, and then continue on. That's the one thing that's nice about these video lessons, is you can make them go as fast or as slow as you want. Now, if you find yourself to be a very bad note taker and you don't think it's going to be helpful to actually write your own notes, A, I disagree. I think you should try anyway. But B, okay, I understand. Well, with every video lesson, I will always take pictures of my own notes and I will put them directly below the video. So before watching the video, you have the option to just print my copy of the notes, and then you can write in additional helpful information. Maybe there's something that I'll actually talk about, but I won't write down on the paper by you writing down those additional things. You can actually have written down the things that I talk about that I don't actually write down, if that's what would help you. Well, anyway, let's go ahead and get into today's lesson. And today's lesson is in section 3.2 out of your Algebra 2 book, 3.2, Linear Equations. Now, below the link for this video, there was a link to for a worksheet that actually goes with this lesson. That worksheet looks like this. It's about independent and dependent variables using domain and range, and then an example. So what I'd like for you to do right now is to pause this video, read through this example through this page, and see if you can try out this example. And in 10 seconds, I am going to start working through this example. So pause this now, and once you're done trying this out, play it again, and you can watch me work through this example. Or you could work through this example with me. You could watch me do it afterwards. You can watch me do this example, and then you do the example on your own. Whatever you think would make it work, this lesson work for you. Try it out. But first things first, read about independent, dependent variables and domain and range. 10-second break goes now. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10-second break is over. Let's take a look at this example. All right. We are planting a small tree in our front yard, and we're going to feed and water it regularly. 1 month after you planted the tree, it's 6 feet tall, and 5 months after you plant the tree, it's 14 feet tall. So the first question we need to ask ourselves is, what is the independent and dependent variables for this situation? And if we go back to those definitions, it's kind of easier to locate the dependent variable first. The dependent variable is the variable that depends on the other variable. And when we think about this situation, it's either that time is affecting the height of the tree, or the height of the tree is affecting the time. Well, when you think about it, it's time that will determine the height of the tree. So, for the dependent variable, in this particular case, it is the height of the tree. Now, whenever you're talking about height, how are we measuring height? Are we talking inches, feet, miles? I don't know. So you got to label it. And in this particular case, it looks like we're talking about the height of the tree in feet, so you should label it in feet. Now, the height of the tree depends on the amount of time that has passed. That means that time is the independent variable. But same thing. By time, are we talking seconds, hours, months, days, years? I don't know. Well, in this particular problem, what's this? Oh, 1 month. So in this particular case, time is being measured in months. Okay, now reasonable domains and ranges for it. Domain is the set of possible values of the independent variable. Well, this particular problem, the way that we wrote it, we started this at 1 month after you planted the tree, and we don't actually know how tall the tree was when we actually planted it. We only know how tall it was at 1 month. So a reasonable bottom value for a domain would be 1. Oops, I forgot to label domain. So 1 is a reasonable bottom value for the domain. Now what about a reasonable top value for the domain? Well, how long is this tree going to live? A year? 10 years? 100 years? I'm not really sure, but I know that if you think about things like redwood trees live for several hundred years. So to be safe, I'm going to put in 1,000, just to make sure. So I believe it's possible for a tree to live to be 1,000 years old. So I'm going to have a reasonable domain for me is to be 1 to 1,000. Now, as far as the range goes, well, I know that trees grow. That's the general nature of trees. And the bottom height that they tell us about is 6 feet. So I know the bottom part of the range, but I don't really know what the top part of my range is until I actually go and solve part C first. So part C is to write a linear equation that describes the situation in intercept form. Now, I talked about this a little bit yesterday. I want to urge you to not think intercept form, but to think point-slope form. Point-slope form is y equals m, the slope, times x minus x1 plus y1. And in this particular case, because, actually I still need to figure out what the slope is, because it doesn't really tell me what the slope is, it just gives me this. Well, slope. I'm going to have to use my slope formula. Let me get into my next page of notes here, and let's write in some valuable information here. This is section 3.2 linear equations. Let me first mention our slope. The letter that's frequently used for slope is x, or excuse me, is m. And your formula, you've used this in algebra before, is y2 minus y1 all over x2 minus x1. This is, of course, if you're given a couple coordinates and those coordinates look like x1, y1, and x2, y2. One question I always get asked is, do you have to go 0.2 minus 0.1? And the answer to that is no. You can also go 0.1 minus 0.2. But what's important is to be consistent on the numerator and denominator. If you go y2 minus y1 on the numerator, you got to go x2 minus x1 on the denominator. Or if you go y1 minus y2 on the numerator, you need to go x1 minus x2 on the denominator. Anyway, back to my problem over here. My slope in this particular case, I don't have much room, so I'm going to do my work over here. So my two coordinates, 1 month, it's 6 feet tall. So my first coordinate is 1, 6. 5 months after you planted the tree, so that's after 5 months, it's now 14 feet tall. So my slope, y2 minus y1 over x2 minus x1. 14 minus 6 is 8. 5 minus 1 is 4. And 8 divided by 4 is equal to 2. So that's my slope. So heading back into my point slope form, I'm going to put in this 2 for the m. And then I need to put in a point. It doesn't matter which point I put in. I could put in 1, 6 or 5, 14. I'm going to choose 1, 6 because the numbers are smaller. So x minus 1 plus 6. And now, just do a little bit more math. 2 times x minus 1, that gives me 2x, 2 times x is 2x, 2 times negative 1 is negative 2, so minus 2, plus 6, and this is equal to, you got some x's and some numbers, and you can't combine numbers with letters, so I just have to go my -2 plus 6, which is 4. And my final equation is y equals 2x plus 4. And that's using point slope form, but then just doing a little bit of extra math to end up at y equals 2x plus 4. And if we look at intercept form, it's also sometimes called slope intercept form. Anyway, slope intercept form or just intercept form is y equals mx plus b, where m stands for the slope, b stands for the y-intercept, and if you look at my point slope form equation, 2x plus 4, that is slope intercept form. So just doing point slope form with a little extra math, I ended up in slope intercept form. So this is a linear equation that describes the situation in intercept form. Y equals 2x plus 4 is my equation. And then you always need to identify those variables too. So x equals time in months. So I'm having to write a little small here. I'm running out of space. And y is the height of the tree in feet. Okay, now I've answered part 1 and I've answered part 3. The last thing I forgot is to do the top end of my range. But I want to use my equation for this, and I'm going to use that domain that I talked about earlier. So if I have y equals 2x plus 4, I need to figure out what the height of that, because if this tree is going to keep getting taller and taller and taller as time moves on, you can plug the top value of your domain into your equation, and that'll kind of tell you what the height is at the end of your domain, which will be the top of the range. So in this particular case, I have 2 times 1,000 plus 4, and this ends up being 2 times 1,000 is 2,000 plus 4, which is 2,000. So 2,000 feet. So with that said, perhaps my domain and range are a little bit inaccurate. I've never seen or heard of a 2,000-foot tree. That seems way too tall. So maybe my domain was a little bit long, but it still seems reasonable to me for a tree to live for 1,000 years, maybe. So I'm going to actually keep that domain and range. But if you ever have to come up with a domain and range, you should have kind of a reason why you would consider those numbers to be what they are. So that is this pure example. So very nice. Heading back into our notes, we had the slope formula. It would be helpful to just write out these formulas if you haven't already. Point slope form once again, y equals m times x minus x1 plus y1. And for this one, you are given m, and you're given x1, y1. You need to be given this information in order to plug them in to the equation. That's point slope, and then there's slope intercept, or some people just call it intercept. Some people call it y-intercept form. It's all kind of the same thing. That's y equals mx plus b. And for this one, you need to be given the slope, which is equal to m. But then you also need to know the y-intercept, and the y-intercept is 0, b. It is whatever the y-coordinate when the x-coordinate is 0. And if we go back to this problem that I actually worked on just a minute ago, because I didn't have the y-intercept, that's even a better reason to use point slope, because then you don't have to worry about exactly what is the y-intercept. As you work out the math, it gets worked out here. Because the b is equal to 4, you know that we have a y-intercept at the coordinate 0, 4. Okay, I have some examples for you. Example 1. Write an equation of the given graph. Write an equation of the given graph, and I have a graph for you. I put it on graph paper, and that graph is right here. I'm going to use point slope form, and I first got to figure out the slope. You always want to find a couple points that go through nice corners on your graph paper, and I like to do the little box thing where I just draw a vertical line down from this one and then a horizontal to this one to lead from point to point, count up the squares. This is a distance of 3, this is a distance of 2. That means that the slope is, if you've ever heard the term rise over run, that's what we're going to use. The rise is 3, the run is 2. Now what about positive negative? Well, in this particular case, as you travel from left to right, the slope is downhill. Downhill means negative slope, so this is a slope of -3. Then if I'm going to use point slope form, I also need to figure out a coordinate of this graph, and it appears that this coordinate right here is 2, 1, 2, 3, 4, 5, 6, 2, 6. So I'm going to use this slope and this point and put them into point slope form. Y equals, if we use this from earlier, our m, so -3/2 times x minus x1, and the x coordinate was 2, the y coordinate was 6, so it's x minus 2 plus 6. Now, this is an equation for this graph, and it's a good equation. A point slope equation is a legitimate answer. The one problem with this point slope answer is that when you look in tonight's homework, the answer keys actually won't be in point slope form. They'll be in slope intercept form. So on a quiz or a test, unless it says slope intercept form, you can use point slope form. But if you have to then get it into slope intercept form for answer checking, or just because you prefer it, you have to distribute -3/2 times x is -3/2x, -3/2 or -1.5 times -2 is +3, and then plus this 6, and I left out my x, so put that x in there, and then your final answer would be -3/2x plus 9. So like I said, I am okay with this point slope answer, but if you want to be able to check your answers, you might need to go into slope intercept form from there to make sure that you have that right answer. And that's example 1. Example 2. So how do you go about writing an equation when you're given 2 points? So write an equation, a linear equation. I should probably write that in there. A linear equation given 2 points, 2, 3, and -4/8. You actually saw me do a problem like this when I was doing that story problem off that worksheet a couple minutes ago. We start off with our slope formula, and we plug these 2 points into the slope, 8 minus 3 all over -4 minus 2. In this particular case, 8 minus 3 is 5, -4 minus 2 is -6. A positive divided by negative is a negative, so -5/6. So this is my slope, this is my point, plug it all in. Y equals m, -5/6 times x minus 2 plus 3. And I'm going to leave this answer just like that because a point slope form answer is a good answer. Example number 3. Let's find the slope of an equation. So if they tell us that the equation is 6x minus 7y equals 21, how do we go about finding the slope of this? Well, if we look back at our equations, whether you're in point slope or slope intercept, the slope, the m, it's pretty much whatever's hanging out with the x when y is solved by itself. So we're going to take this equation, solve it for y. First, subtract 6x from both sides. Don't forget about this negative. Negative 7y equals negative 6x. 21 is positive, so plus 21. I then divide everything in the equation by negative 7, and y equals, and I'm going to handle these individually. Negative divided by negative is a positive, but 6 and 7 do not divide evenly. So it's positive 6 over 7x, and then positive 21 divided by negative 7 is negative 3, so minus 3. So I have a slope-intercept answer now, and 6 over 7 is what's hanging out with the x. That's my m, so that's my slope. Make sure you answer it in a way that's clear to the whoever it's grading it. In this particular case, the slope is 6 over 7. All right, two more quick examples. And these next two examples deal with parallel and perpendicular lines. So number 4, what's the story with parallel lines? And number 5, what's the deal with perpendicular lines? Wait, I spelled perpendicular wrong. Start over. Perpendicular. Perpendicular. Okay. What's the deal with parallel lines and perpendicular lines? Well, I have graph paper examples here for you. If you take a look at this graph here, the two lines do appear to be parallel. They are. I drew it. And if we find the slope of these two lines, run, rise, this one has a slope of positive 2 over 3, a run of 3, a rise of 2. The graph is uphill. Same thing, this graph is uphill. A run of 3, a rise of 2. The slope is also positive 2 over 3. So what's that tell us about the slopes of parallel lines? They're equal. They're equivalent. So parallel lines, slopes are equal. Don't say slopes are the same. It's kind of vague. Same is different. No, wait, same is same. But if they're two different lines, can they have the same slope or do they have equal slopes? It's confusing, isn't it? So we're just going to say slopes are equal. Let's take a look at perpendicular lines. I drew this graph here, and if you look, you could use a protractor, but what you have here are 4 90-degree angles, which means that these lines are parallel. And if I found the slope of these, from this line, this point to this point, run of 1, rise of 3, so the slope is uphill, so positive 3 over 1. This particular graph, going from this point to this point, a rise of 1, a run of 3, but it's going downhill, so it's negative, so the slope would be negative 1 over 3. So when two lines are parallel, notice we got a 3 over 1 and a 1 over 3. These are reciprocals. One is positive, one of them is negative. So what this is referred to is negative reciprocals. So slopes are negative reciprocals. And I'm concerned that when you look at negative reciprocals a week or a month ago, you might not remember what that means. So put it like this, that if M1, if the slope of the first line is positive 3 over 2, the slope of the other one, they need to be negative of each other. So if one of them is positive, the other one's negative. They also need to be reciprocals. If this one is 3 over 2, this one would be 2 over 3, or negative 2 over 3. And that is how slopes of perpendicular lines work out. Okay, students, at this point, this is it for the Wednesday night. Just want to make sure that you understand what's going on with this lesson. If you look onto the Excel spreadsheet where the calendar is, that'll talk about the practice problems we're going to be working on in class tomorrow. You can find them in the links directly below this video. And have yourself a great Wednesday night. This is the only time this year I'm going to make you watch 2 videos in one day, so I'm sorry that it took up a lot of your time tonight, but it will not happen again because from here on out there should only be 1 video per day. Thank you very much. Have a great Wednesday night, and I'll see you tomorrow on Thursday. Bye, everybody.